So we have 4 talks today. It's going to be very difficult timing to keep everyone to time because there's such a lot of interesting things to be said. We want to have a little bit of time at the end for our discussion, but we have to finish at 5 o'clock. So without more ado, I guess I should get the thing rolling. We are recording the meeting. If anyone has any objection with that, please send a message to me in the chat. I'm Shirley Coleman and I'm chairing the meeting and trying to keep everyone in order here. So we're thrilled to have 2 speakers from the History of Statistics section of the Royal Statistical Society and 2 speakers from the Quality Improvement section of the Royal Statistical Society. We have 3 people online, one in the United States, one in Southampton, one elsewhere in Britain, and one person live who's sitting next to me, Jonathan, and he'll be the 3rd speaker. So I think we'd better get going. First of all, it's my great pleasure to welcome Penny Reynolds, and she's joining us from University of Florida. Penny actually has been trained in engineering statistics, is currently working in College of Medicine in University of Florida, and is going to fill us in with some of the earlier work of Shewhart, and as it says, his Epiphany, Evolution and Eclipse. And I'd like to hand over to Penny, who will be followed by our 2nd History of Statistics speaker. Okay, Penny, over to you then, please.
Okay, thank you, Shirley, appreciate it. So, Walter Edwards Deming always used to say that the control chart was actually the least of Shewart's accomplishments. What he really did was give us a sound mathematical foundation for the study of process and process control, but also the statistical tools to operationalize systems and also enable us to make decisions as to whether a process was stable or out of control. So today I'm going to talk about his thinking, which led up to the epiphany of the control chart, how his thinking evolved after the control chart, and then a brief discussion as to why, even though it's so brilliant and seems so obvious to us 100 years later, why it took so long to catch on and actually nearly disappeared several times. So just a brief thumbnail biography. Walter Shewhart was an American. He was a physicist by training and a self-taught statistician. He was a farm kid from Illinois, and even though his father only had about 4 weeks of formal education altogether, he really valued it for his son. And so Shewart's education at the University of Illinois Urbana and later UC Berkeley was funded almost entirely by the Bank of Dad, which caused a lot of consternation amongst various nebby neighbors and relatives who couldn't understand why you'd want to spend money on something which didn't help you milk cows properly. After a brief stint of teaching after graduation, he spent his entire working life in the American telephone telegraph system, first of all at Western Electric in Cicero, Illinois, and later, after corporate restructuring in 1925, he went to the Bell Telephone Laboratories, which was the R&D arm. In the last 20 or so years of his life, he spent a lot of time consulting, mostly on quality matters, but also in establishing the Institute of Mathematical Statistics. And he was a founder and an enormously influential editor of the Wiley series in Probability and Statistics, which was the first actual library of statistics references since the 18th century. So how did the control chart come about? Well, P.C. Malinobis always used to go around saying that it was overnight, but it really wasn't. It did come together quite quickly over a matter of a few days, but he actually was thinking about it for approximately a decade. And it involved 4 major strands of thought: that isolated observations are not the same as information. How do you tell what an anomaly is? Some data are always better than no data at all. And cutting edge is not the same thing as useful. So the first insight was that you cannot interpret an isolated observation. Occurred in 1916 when he was a summer student at Western Electric, and he was flagged up by the doctors as having tuberculosis. Now, in those days, TB was a major public health scourge, but doctors only had virtually nothing in the way of tools for either diagnosis and treatment. The only thing they could do is take a temperature and hoped it was an early enough signal of disease. But Shewhart knew he wasn't ill. He had no risk factors. So his solution was to take several measurements of his own temperature over several days and other people's temperatures, and was able to show that the temperature that had been flagged up as being a signal of disease was nothing of the sort. His second insight as to how you define an anomaly came during his PhD work at UC Berkeley. It was a very clever extension of Robert Millikan's Nobel Prize-winning work on establishing the quantum properties of atoms. He measured the charge of an electron based on counterforces of gravity and viscosity of the medium. Shewhart added sound waves to that. The problem was, if you read his dissertation, you can see how frustrated he must have been. It's just tables and tables and tables of numbers comparing his observations with what was expected from theory. The straight line graph here is from Millikan, and it was just fitted by eye. So there was no, regression was not really known in those days. There was no formal measures of variation, no way of establishing whether or not you were measuring a signal or if it was just a function of measurement error. And these experiments were very difficult to do. It also turned out subsequently that Millikan not only gracefully tidied up his data so it would fit what he expected, he also pinched the vast majority of the information from his student Harvey Fletcher, who was denied a co-authorship, and therefore the Nobel Prize was a quid pro quo for getting his PhD. The third insight was that some data are better than no data at all. In other words, priors should be driven by data to be useful. And this was his first job after leaving university. He had to develop a soundproof helmet shield for pilots. This is in the days of open cockpits, you know, Sopwith Camels and Tiger Moths. His line manager plopped the order on his desk with the expectation that Shewhart would have the specifications for different human heads on his desk by tomorrow. So what Shewhart did was sit up until 4 o'clock the next morning, reading a statistics book, the only one he could find, which was by an economist called Wilfred King. Then he rushed out the next morning as soon as the plant opened to measure heads of about 100 workers that he could find, did the maths, got the job done by that afternoon. And finally, cutting edge methods are not only always useful, especially if they're highly mathematical and not directly applicable. He really learned that working in the Bell system. They had some of the leading brilliant minds in mathematics and physics of the time, people like Malcolm Rorty, Ed Molina, who independently rediscovered the Poisson distribution. They also had charts, which they used to plot defects. But as you can see from the chart on the left, they're not easy to use at all. They're very difficult to understand. And these are the days of mechanical calculators and side rules, which could not calculate cross products. So it involved hours of tedious calculations. So they didn't tell you what to do, and it was really hard to figure out what they were telling you. So finally, in that week before the memo, Shewart's ideas came together in what he later defined as the fundamental problem, is that quality control is developing an operation that will produce whatever it is that has the quality characteristic that we think is important to meet the needs of the system. And the idea of the tolerance range, if the observations repeated once or an infinite number of times. So he started with the process, not the specs, and that the process should be stable and repeatable, and we have to be able to tell the difference between a stable process, one that is out of control, by a notion of quality, which is prediction within limits. So how did this thinking evolve after the control chart? Well, there's a flurry of creative activity from him in the next few years. He wrote between 10 and 12 technical reports. He summarized all his thinking in 2 books, the 1931 magnum opus, which is Economic Control of Quality of Manufactured Products, say that quickly, And then 1939, it was a distillation of his lecture notes to MIT in the Department of Agriculture, which was edited by Deming. So his ideas evolved from the control chart in terms of variation, statistical operationalization, visualizing data as a tool, and the whole concept itself of statistical control. And this is the single most brilliant idea that he really had, was that all processes exhibit variation, and statisticians, we know that. His insight was that not all variation is the same. There's the variation which is intrinsic to the system, which he called common or chance cause variation. No action is required by the operator. However, there's a second source of variation, assignable or special cause variation, which is a signal that something is wrong. So the clue, or the key rather, to statistical process control is to be able to discriminate between those two types of variation, then do something about the special cause variation. Then once statistical control is achieved, we can not only predict future output, but we can manage the system economically, because we don't have to stop the system every so often to correct defects. His second big idea was to apply cutting-edge statistical theory. And this was 100 years ago, when the whole idea of statistics was just tables of numbers. But he applied the first mathematical statistics theory to practical processes and practical problems, not only to characterize the system, but to judge the system in terms of discriminating between signal, the real things we're interested in, or chance noise, and develop the idea of statistical limits. So he described 4 criteria in his book. Criterion 1 is just based on simple summary statistics: mean, standard deviation, range, slope, correlation. His second criteria for detecting anomaly, he developed the 3 sigma rule. The third criterion was detecting drift in processes by fitting of cubic polynomial and then applying fairly stringent goodness of fit tests to assess the significance of the trend. And then finally, criterion 4 is the detection of what we now call lurking variables, or some common causes underlying covariation in even quite short series. Third idea was that you have to look at your data to control the system, or in the words of Yogi Berra, you can see a lot just by looking. And so he used a whole series of complementary charts to identify problems, not just the raw series as on the left, but also in terms of summary statistics like percentage, the average, standard deviation, skewness trend, and chi-square. Most of these were later dropped because they weren't practical. And finally, his whole idea of statistical control was not just the post hoc determination of defects, but it was actually a rule of behavior for the operators. So we're asking the question, when does the operator need to act? The answer is when the process goes outside these predetermined statistical limits. Not just in the case of, say, on the left, where we see a raw sequence of observations, but also in cases as on the right, where an average, a statistical average, just has no meaning as a gauge of performance. In this case, it is the deviations from average of 8 machine shops on the floor. So an average doesn't mean anything here, but you can see that the output of these shops is not consistent. And it's quite easy to communicate that. So what led to to his thinking? Well, there's 2 major areas where he was quite well read, and that was mathematical statistics to understand the nature of variation, but also the particularly American philosophical school of conceptual pragmatism, which led to his theory of knowledge. Howard Hotelling said that he was revolutionary in his application of mathematical statistics. And again, this is the days when there really weren't too many resources in terms of books or papers. And he read everything he could find. First of all, he started with the economists, Wilfred King and Horace Seacrest. But then he got into the primary literature, Arthur Bowley, Francis Edgeworth, and then Carl Pearson, and he became an instant fanboy. He was so keen that after the war, he wanted to rush off to London to study with Carl Pearson, but he was talked out of it, rather surprisingly, by Henry Reitz, who was the top man in statistics in America at the time, because he said statistics wasn't going to go anywhere in terms of job prospects. My thinking about this is what Reitz meant was that practical applications would sully the purity of mathematics. And so that's probably why he wasn't so keen on Shewhart to go to London. I don't know. Nobody really knows why he would say that. But Walter Shewhart was one of the few with the mathematical chops to really take advantage of these, especially the Pearson School of Applied Statistics. And according to Howard Hochtelling, who did not tolerate fools, he said he was the man, describing the system, distribution, central tendency, variation, discriminating patterns, regression, correlation, goodness of fit, and most importantly, defining thresholds. He developed the idea of the tolerance range versus confidence intervals, but he did explore the Pearson-Neyman lemma. Now we know this as type 1 and type 2 errors for distinguishing between false positives, false negatives. He realized that unlike the early times in the Bell Labs, you don't have to come up with a new distribution every time because physical processes are rarely Gaussian. But if you've got a large enough sample, they will conform to a normal distribution. And finally, he worked on applications of Chebyshev's inequality to come up with his bounds for any probability distribution, and which led indirectly to the 3 sigma rule. The second thing was the role of philosophy, or how we know something. And he got really keen on a fairly obscure American philosopher called Clarence Irving Lewis. Now, they did overlap at Berkeley, but Shewhart discovered Lewis's book, Mind in the World Order, when Lewis was a professor at Harvard. And he was the founder of conceptual pragmatism. Now, Shewhart said it took him about 14 rereads to really grasp the concept of what Lewis said. Most people don't have that kind of patience. Lewis is an extremely difficult read. It's one of the few books that put me to sleep in about 5 sentences. But from what I can gather, these were the 3 key ideas that Shewhart was able to obtain. First of all, that knowledge is facts with context. So that's where his isolated observations idea came from. And Shewhart was very keen on what he called operational definitions. So even if it's tentative, you need something to start with, a prior, in order to interpret what you see next. Secondly, and this is key, is that knowledge requires the judgment of sequences of events. The past has predictive knowledge. We can use our knowledge of the past system because the future comes from the past. Then what matters is what we see in front of us right now. Does what we see conform or depart from what we know from previous observations? And finally, knowledge is iterative. Now, this concept requiring continuous comparison of your sequences, updating as new knowledge becomes available. This was really developed further by George Box in sequential experimentation, and Box together with Norm Draper in evolutionary operation theory. And then finally, knowledge requires action. So in order for knowledge to be knowledge, we have to act on it. And so that leads to the whole concept of decision criteria. Now, even though this is so brilliant, it took a really long time to get established. So the first rule of history in homicide is you need a timeline. And you see that there's been, after Shewart's initial incubation period, development of the control chart in May 1924, There was a flurry of activity on his part, culminating in the American Statistical Association meeting with numerous sessions on quality. But you see that it's bracketed between two global wars and the Great Depression. After the Second World War, there was a flurry of theoretical development of process studies, Hotelling with his T-squared chart, Abraham Walt, George Barnard independently developing sequential ratio tests, Ewan Page and cumulative sums. But there's virtually nothing going on in America. Deming went to Japan, where quality control took off. Shewhart himself visited Mahalanobis in India, where quality control took off. Nothing in the United States until the energy crisis in the 70s, and then 1980, Deming mania started, and the US woke up to quality control. So to understand this phenomenon, we really have to understand or discover why practice innovation gains traction if it does. And there's three pillars to that. There's motivation, the influence or networks of the idea person, and how well the person communicates. The first was that it took so long in the United States to become established because there's absolutely no motivation whatsoever. Status quo bias. Europe and then later Japan had been devastated by the wars. US manufacturing was the only game in town. There's absolutely no competition, so they could afford to swan about because everybody had to come to them. Now, in the wartime, efficiency and effectiveness were prioritized, so there was increased interest in quality control then. But after the war, with the shift from military to suburban luxury items, well, customer complaints about poor quality were just the cost of doing business. The whole goal of manufacturing at the time was just to make a lot of money, and quality was seen as interfering with that. Then came the 70s, the energy crisis. US auto industry realized that they were lagging well behind Japan in the production of compact, fuel-efficient cars instead of the big monsters they used to have. Japan was eating their lunch. And then 1980, the NBC documentary came out featuring the 80-year-old William Edwards Deming. Deming mania took off and quality control became a feature of US manufacturing. So why was this? Well, when we talk about influence, we have to ask who are the stakeholders. So it seems obvious to us because the folks at the time who loved it were people like us. They were statisticians, mathematicians, engineers, military, government. They had a stake in it to be efficient, at least during wartime. And Shewhart rightly got a lot of professional recognition for his contributions. American Statistical Association, ASQ, the Royal Statistical Society. He was president not only of ASA, but also the Institute of Mathematical Statistics twice. Speaking gigs all over the place, consulting gigs. The tech bros and the policy wonks were kind of mystified, really. One of the most telling quotations I found from a review of Shewart's book, Economic Control. This quote was pinched apparently from Abraham Lincoln, but they summed it, the whole book, that brilliant book, as saying, some people like that sort of thing. Anyone who likes that sort of thing would like that sort of thing very much. So praising with faint dams. But what was absolutely key is who hated it. And that's the people who actually did the work, the production line workers and the bosses. Workers were paid for piecework. They had to turn out as much as they could, as fast as they could. Leadership didn't care about quality. They wanted to make money, and quality just slowed things down. And then when control charts had been introduced, especially at Western Electric, they were weaponized just to punish workers for producing defects. So nobody wanted to use them, and the unions, in fact, voted them out. And finally, the big one was communication. Shewhart was apparently a really lovely man, really kind and really soft-spoken, but he could not explain things at all well. Deming said he had an uncanny ability to make things difficult. And Joe Juran, who is no fan and found it difficult to be nice to anyone, said it was like talking to someone from another planet. The reason is because Shewhart's ideas did not help the people who actually had to do the work. He hadn't actually worked in a factory, so he didn't have any street cred. And then the people who were doing the work were mostly unskilled. They couldn't speak English particularly well, most of them. They were working in horrible sweatshop conditions. Deming was once told that he should never ever be caught in a stairwell at shift change at Western Electric because he would have been trampled to a pulp. People were just trying to get out of there. No investment in the work. And then when Shewhart spoke, and especially when he wrote, it was far too mathy and complicated. The maths was, for the charts were still really difficult and had to go back to process engineers and statisticians. So everything had to be held up while people figured it out. And his writing was truly horrible. He was vague, he was obscure, he'd go chasing off after rabbit holes of interest. Too much detail, really disorganized. Like his first technical report explaining the control chart in detail was 45 pages long. And about 5 pages of that, he's banging on about Carl Pearson's skull collection, which is not interesting and not helpful. Fortunately, he had two champions. And the one, of course, was Deming, which all of us are familiar with. So he always said that just trying to understand what Shewhart wrote and what he said took him all his time to reinterpret, and then he'd have to write it out again so he could extract what would make it unique for him. But over 50 years, he extended Shewhart's ideas, not just to manufacturing, but also to the census administration and management. The second champion is one no one's ever heard of, and that is Bonnie Small, who was noted in the ASQC for explaining Shewhart better than Shewhart. Just a very brief biography, since nobody's heard of her. She graduated in 1930 from the University of Wisconsin-Madison, my alma mater. She was a very gifted mathematician, and she wanted to major in physics, but in the 1920s, the administrators just clutched their pearls at the idea of a girl being in a classroom of men. And also the thinking at the time was that women in the physics department lowered the tone. So she had to take a major in classics, and she was allowed to take a minor in physics. So after she graduated, she went to work in Chicago in her cousin's photography business, but she used to go to the library all the time to keep up with her reading in physics and maths. She read Shewhart, became a convert to control charts, applied them to her cousin's photography business, where she said they worked like magic to tell you what was going on. In 1942, after the United States entered the war, more women were being recruited, and so she joined Western Electric as the first quality manager. She got through the door by sheer cheek, past security, past human resources, got an interview with a process engineer, and was able to persuade him that she actually knew how to implement control charts. She was then the project leader in the 1956 Western Electric Quality Handbook, and the number of control charts went from 0 to over 5,000 throughout the entire complex. So what she did really was to show up a major weakness in Shewhart's thinking, and that was that he was very slow to recognize that it's not enough to have good statistical methods. Yes, it's true, they realize the hidden anomalies that might be lurking there, and that's what the maths are for. But in order to identify what the root cause of those anomalies, you really have to know the system. And so Bonnie Small made the methods simple enough so that production teams could apply them correctly and consistently, hence the development of the X bar and the R charts alone instead of all the complicated charts that Shewhart wanted. She also rewrote Shewhart's 4 criteria, which became the Western Electric rules for detecting out of control conditions. And as this diagram from the handbook shows, she actually gave working examples for how you could use these charts to pinpoint actual physical problems, such as oversized parts or a meter needing repair, to explain deviations in the system. So what can we learn from this brief history? Well, first of all, the power of statistical method. Decision-making should be data-driven, the importance of variance reduction, the importance of standardization, and the mindset of continuous improvement. But it's not enough to have brilliant statistical methods. You need clear communication, you need champions, and unfortunately, you usually need a crisis to nudge people into change. So I've provided at the end a bunch of readings. The most important is the Indian Statistical Institute has all of Shewhart's writings free online. And here's a couple of other background references.
Thank you, Penny. That was really fascinating review of background. Who would have believed that there was such a deep sort of evolution from Shewhart? That's fantastic. Thank you. Slides will be made available. We will have the recording. So I think we had better move on to our next speaker, but thank you very much. Penny mentioned about Shewhart being interested in Pearson and wanted to come to the UK. And our next speaker, John Aldridge, is going to talk about how Shewhart had dealings with the Royal Statistical Society. Hey, everyone. Thank you for that brilliant talk. We're going to move on actually to Jonathan now, who's going to talk about practical aspects of Shewhart's control chart and raise a few controversial issues, no doubt. And I will hand over. Jonathan is chair of the Quality Improvement section. Let's get this. There we are. And over to Jonathan.
All right. Hello. You can't see me. I'm behind the camera, but I suppose I could do one of these. And I'm there now. So, yeah, Jonathan Smythe-Renshaw. I'm the chair of the Quality Improvement Group, as Shirley said. So, I have prepared some things for you to think about SPC. And so here we go. Here we have the Ford plant in 1924. So this is typical of production at the time. And it may explain why Shewhart and others were thinking the way they did, and were exploring different ways of controlling production to ensure quality. And it is also possible that batch production was the thinking behind his X bar and R charts, because it was 20 years until the individual chart was proposed, and it wasn't proposed by either Shewhart or Deming, though the idea was there. And to this date, automotive industry has had a large influence on the use of SPC. And it has been vocal in a number of assumptions that I've experienced myself. So, for example, using X bar and R charts with a sample size of 5. So, for example, people will take a sample of 5 at the beginning of every hour. And they'll just be using that because they're assuming normality. And they want to use the assumptions around normality. There are other areas included, which I will also discuss. This includes not plotting autocorrelated data, which is something that I know Roland's going to talk about as well. However, these assumptions still to this day shape SPC. And today I'll attempt you to, if you do think this way, to move away from that way of thinking and not disappoint Shewhart by retraining your thinking. Because as Deming said at Shewhart's funeral, he knew disappointment and frustration through the failure of many writers in mathematical statistics to understand his point of view. So we are going to change that today. So the next area you see here, this is the US government and their use of a new calculating machine to determine the bonuses of First World War veterans. And it's the computing department. So the role of computers, in particular the use of statistical software packages for SPC, have, in my opinion, made a major impact on the use of SPC and its teaching. As we will see in this talk, a simple yet most powerful use of SPC can be achieved with primary school maths. And this doesn't sell software packages to businesses. But if you add some complexity, well, you know, people are obviously going to be interested in buying the packages. However, the role of computers they do have a role to play, and I've done some action research, which I will talk about on this topic, and we'll see how computers can be used and where they should be used. So Shewhart's book is about the economic control, not statistical control. And it's not an easy read. However, it does provide a very detailed account of Shewhart and his colleagues' thinking. And the index is an interesting place to look in any book. And we see that the most referenced person in the book is Shewhart and his rule of data, which I will talk about shortly. And it seems to me that if you read between the lines for Shewhart and his colleagues, they used the empirical rule of data to present an economic argument. But this world could also be underpinned with statistics. But Shewhart, in my opinion, concluded that both were correct. But one was very simple and profound, and the other was complex, and maybe a way to explain the profanity, but the complexity would block the revolution of control charts, as Penny's spoken about. The book does discuss the use of the mean, the standard deviation, the skew, and kurtosis. So this is Shewhart's inequality, and the limits are shown here. And then we see the use of the mean, the standard deviation, the skew, and kurtosis. But we as statisticians are fully au fait with these descriptors, and we don't need to really dwell on this. So if we bring the thinking behind the empirical rule of data to more recent work, we can see that Don Wheeler has done a lot of work on trying to understand the relationship between kurtosis and skew. And he actually produced a graph which shows the percentage of 3 sigma coverage for different shapes of distribution. And you can see I've coloured in the green, this is where 98% of data would lie. And in my opinion, most people will see distributions that actually fit, that will cover most of the distributions that people are ever likely to see or encounter. And yes, it does include the normal distribution, of course, but it's only one very small blob in the corner of the graph. So Shewhart, if we look at what Shewhart did, so Shewhart in 1924 with his colleagues provided the foundation for understanding data. But why has it not been embraced? Well, so Penny alluded to some of the reasons why. To try and explain this is obviously profound. And obviously today, it would be great if today led to the wider expansion of the use of SPC, and that when we look back in another 100 years' time, we can say that today was the day when people embraced SPC and it became much more common knowledge. So to start this journey, we need to think about what Shewhart did. Now, Shewhart had an experiment where he got people to write the letter A. So if I asked you, if you're online, if you wrote a list of 10 A's on a piece of paper and you looked at your 10As, are they all the same? And the answer is likely to be they're slightly different. Now, if somebody next to you has drawn the letter A's and you look at their letter A's, then they'll be different from yours. So what you've got is this idea that we have variation. So what we already know, so our first lesson is that variation is everywhere and it's always present. Another thing that Shewhart focused on was the use of proportion charts. Well, we know better than that today, and we can forgive him for that and move on. So he also used X bar and R charts. He was unable to see the subgroup of 1. And neither Deming, this is according to Wheeler, Don Wheeler says that Deming couldn't see it either. And he had a discussion with him in the late 20th century, and having met Don Wheeler and seen Deming in person, Deming on YouTube, I can imagine I had a very, very interesting conversation. And again, we know better. So the other area where Shewhart worked was autocorrelation. So he plotted autocorrelated data. If I just flick forward one slide, you can see that, again, work has been done to show the adjustment factor. This is for an individual's chart, where you can see that highly correlated data can be plotted on a control chart, and there is an adjustment factor that can be applied to your control limits. But really, if you look at it, the effect only really matters when you have an absolute correlation above sort of 0.7. So the other thing to think about here is, if you have highly correlated data, we also have the scatter plot. So the idea behind control charts is to look for relationships. And again, the scatter plot can also provide information about relationships between values. He used the empirical rule of data, and I've already spoken about the work of Shewhart. The other area was rational subgroups. Now, this is very important. So Shewhart wrote that measurements of phenomenon in both social and natural sciences, for the most part, obey neither deterministic nor statistical laws until assignable causes of variation have been found and removed. So what he's basically saying to us is, don't plot. So you don't plot what you know is different and expect to learn new insight. So with the knowledge of variation is everywhere and always present, the empirical rule of data and 3 sigma coverage, autocorrelation is unlikely to matter, and rational subgroups, what is missing? So what is missing is the idea of successive differences, or the moving range, which allows us to achieve the subgroup size of 1. Now, the history of this can be traced back to the successive differences linked to determining the range of field artillery, and this is from 1894. So with this missing piece of data, we can provide a timeline for the individual and moving range charts. So I present this here. So in 1942, Jeanette, he doesn't mention individual moving range charts, but we see that in 1953, that Keane and Page, they credit him with actually having come up with the idea. So we know we can trace this back to Jeanette. And then you can see that you have the Western Electric work, and then there seems to be an inordinate gap in the knowledge. And then we see the work of Wheeler and Chambers. So this big gap. it's like nothing's happening, but obviously it is, because the 7 quality tools, the IMR chart is one of the quality tools. We've got Six Sigma, and as a quality fad, these have exposed many people to control charts, but they've also exposed many people to statistical packages and complexity. And this is obviously part of the problem. So if we look at the construction of the control chart, originally it was intended to be on paper. So I did some action research with some master students, and they said things like, what's paper? Why do we use paper? So the use of computers, it does need to be engaged to gain a wider acceptance of SPC, but not the complex software. And I found that Excel will work really well, and it will remain ahead. It remains ahead of paper, in my opinion, because people don't make mistakes when they come to do their mathematics. So let's have a look at the calculations. So you can see here I've got a set of data. So the calculations would be that you would collect data in time order, and you would then calculate the moving range. So you calculate the moving range by looking at the first 2 values, and you would look at the absolute difference between the first 2 values. So again, this has been around successive differences, longer, further back than Shewhart. And what we do is we take the positive difference between the 2 readings, and then we look at the next sequence and we take the same difference again. So we know if the MR values are big, then we're going to have lots of variation. If the MR values are small or 0, then we have minimal variation. So we can calculate, back to primary school maths, we can calculate the average of our data, and then we can calculate the average for MR bar. Having these 2 numbers, we can then use the standard formulas where we use what I would refer to as SPC pi 2.66, which is the adjustment made to get closer to the standard deviation. Looking back on that, does it really matter that you make that adjustment? I mean, you could argue that you could just leave that as 3 MR bar, but the adjustment's been made, and it's proposed. So therefore and then what we do once we've actually got these calculations is they allow us to construct the control chart. So here are my A's. Okay, so no, these are my A's, and I've measured a feature on my A's, and what I then do is I then construct the graph by plotting the features for each of the A's in time order. I then calculate X bar as I showed previously, and then I calculate my limits. And having calculated my limits, I'm able to make some assessment of my process. And I can see that in this particular case, because all the data points fall within the control limits that I've constructed, that I can say this process is stable and predictable. And because it's stable and predictable, I can therefore draw the process into the future and then use it to monitor my process. We should teach this to primary school children. We need to start a program of educating people in how to understand what is the most profound technique for allowing people to understand what's going on around them. So there are Western rules for the Western Electric rules. However, I would propose that we need two rules. And the first rule is that if we get 1 point outside the limits, that we stop and investigate. And the second rule is if we have a run of 7 data points above or below the average, that we investigate what's happening. Because some of these things may be happening because we're making them happen by design, by the way we're changing things. And if you work out the probability, the chance of having this one outside here, it's 1 in 100 based around the empirical rule of data most of the time. And the chance of having 7 in a row above or below the average is 1 in 128. So you've got like two simple rules that are roughly 1 in 100. And we should use these rules. So we have the control chart. Shewhart gave us the idea and demonstrated the power. The ideas behind individual moving range charts were developed in the 1940s. So I leave you with this thought. If you're going to use control charts, don't disappoint its creator. But if we are to make progress, we may need to be not gentle and not never ruffled. But what we need to do is make our case with dignity so that we can make a real difference in the way society thinks about the use of control charts. I thank you.
Okay. Hey, thank you very much. Thanks, Jonathan. Lots of good points to think about there. Great. Yeah, if anyone has a quick comment while I'm just changing slides, you're very welcome to.
We have been working with a lot of making data fancy. We've trained 50,000 people in the last 4 years in using the Excel charts. Working very hard to do what you want to do.
Very good.
And all the points you made today, we teach people about variation, we teach them about understanding it's normal and it's not normal. We actually use formals, but two of them aren't too suggesting.
Yeah.
I went to our workspace for weeks, and I've written dozens of tools in Excel, which we share with the NHS. We can put lots of platforms, but to help people just do this themselves on a daily basis.
Very good.
Brilliant. Thank you very much.
Yeah.
John, would you like to? John, could you put your slides up now, please, if you can, and share the screen? And we better move on to the next thought. Thank you very much for that contribution. It's good to hear that you're actually sort of making use of these and getting on with things. We've got two speakers to come. Roland, who you can see on the left there, will be talking about some management issues of control charts. And John's going to talk a bit about the work that Shewhart did with the RSS. If you could get the slides going. Would you like me to put the slides here, John, or will you have them?
Yeah, please.
Okay. Right. There we go. JA. Okay. You want me to run them?
Yes, please.
Okay. Right. So you have 15 minutes as well. Okay. Over to you, John. John Aldridge is sorry, I should say, is in the history of statistics section in the RSS and is connected with the University of Southampton. So thank you, John. Over to you. Yes, you're
Okay,
quite
thank
right.
you.
I keep forgetting to do that just because I can see it. I forget that you can't.
You know, if you go to the top right hand side in the presentation, if you say presenting teams, it should go.
How do it? This one, share. That's the one, isn't it?
You could do that.
You want to go to the windows?
No.
No, no one is on.
It has worked. Is that okay for everyone? Not known any? Sorry, It's very different when you're up here. Right, so there's this one. Right, okay.
So shall I start speaking?
Yes, please. Is that okay, Janina? Yeah, okay. It's my timer. Right, over to you, John.
Sorry.
Okay, so unlike the other speakers, I have no expertise in quality improvement. So I'm coming to this as a new boy.
It's not a chair. Just hold on a minute, John.
Sorry.
Presenting team, so.
Yeah, okay.
That's what I'm having to me. Yeah, it doesn't even work.
Okay. We can do it with brute force, maybe.
We can do it via Teams.
Might be
Just
working.
the share screen.
It's working on it.
I don't know if it's my Wi-Fi connection.
We can do it the brute force way then.
It's up on your screen.
No, that's his.
So we can just share the whole screen sheet. It was out.
Yeah, it's coming on now.
Joy,
We're seeing your presenter mode.
we can switch that now.
That's done.
Okay, John, sorry about that. Over to you.
Okay, thank you. So my expertise is in history of statistics in Britain rather than quality control. So I've got a different perspective from the other speakers. Shewhart had a big impact on stats in Britain. The second slide says what the impact was.
Sorry, minor hitch. If we can do a shift F.
Well, I think I can probably have it. It's going on to a different screen, which is when you put it into present. That will do it. Yeah, you've got better.
Okay, second slide there, John.
Okay, so Shewhart established quality control in British stats, so that's one achievement. More profoundly, he got industrial stats as part of stats rather than as, say, part of engineering. So that was, if like, the achievement. I want to talk to begin with about how it came about. It came about through the intervention of E.S. Pearson, Egon Sharp Pearson, who from 28 onwards interacted with Shewhart. And then Pearson lined up British Standards Institute and Bernard Dudding to give Shewhart a soft landing in British statistics and British institutions. So next slide. So the people involved, I'll be talking about Dudding, who worked for General Electric, who was a sort of British Shewhart. Egon Pearson was an academic at UCL in statistics. Dudding was a bit older than Shewhart, Pearson a bit younger. Next slide. When the RSS was set up in 1834, it was called the Statistical Society of London, and it's really a study of quantitative social science, as we'd call it now. It's basically about social facts, mainly economic facts. So it's really about economic stats and vital stats. And a century later, in 1834, and in 1934, he was still doing the same stuff. In 1934, next slide, please. There's a big change. There's a new journal called Supplement to the Journal of the RSS. Later, 10 years plus later, it became Series B of JRSS, but it originally was the organ of the Industrial and Agricultural section. Shewhart and Pearson were part of the industrial lineup. These were different from the Pearson and was different from the earlier people who joined the RSS because he didn't actually join it to do what they thought of as statistics, which was economic statistics and vital statistics. He joined to do his version of statistics, which was industrial. Behind the agricultural section were ultimately R.A. Fisher and his people at Rothamsted. Next slide, please. How it happened, the first article in the supplement explains this was by Pickard, who was director of the Shirley Institute, which employed Tippett. And he says there's this new interest in the application of stats to industry following some lectures that Shewhart gave in May 1932. So Shewart's lectures in London precipitated the development of an industrial and agricultural section. Next slide, please. The relationship between Pearson and Shewhart. E.S. Pearson was the son of Carl Pearson, and from 1921, he spent his life really in Father Carl's department until Father Carl retires in 1933. Egon had no fixed field of applied stats, unlike his dad, who was seriously interested in biology, hence Biometrica. Shewhart had been applying stats to phone business since the early 20s. He became visible to Pearson, not because of his quality thing, but because he did a robustness study in 1928, which was in ESP's domain. Intersection, they meet when ESP goes to the US on academic business, and he invites Shewhart to lecture in London. Next slide, please. In 1931, Shewhart produced a monumental work called Economic Control of Quality of Manufactured Product. 500 pages, 7 parts, 25 chapters, 3 appendices. Hugely ambitious book, hugely long. One of the features was a 20-page guide in Appendix 3 to literature on science, probability, and stats. He thought of the book as an initial step. So next slide, please. One of Pearson's objectives was to make quality control accessible. So in 1935, he produces for the British Standards Institution a short book. Although Pearson was the academic and Shewhart wasn't, it wasn't at all an academic work because it was produced for the BSI. Pearson and his buddies were very concerned about accessibility and relevance. Shewhart actually apparently wasn't concerned much about accessibility, even though he worked for a company, but the academics were interested. Next slide, please. The effect of creating the industrial and agricultural section was to give industrial statisticians a home. There are 3 of these on the British scene. One of them was student, William Seeley Gossett, who was originally a chemist. Dudding, I've mentioned. and the other was LHC Tippett, who became prominent in RSS, became president of RSS in 1965. So these three all became fellows of the RSS for the first time when the section was created. They weren't in the RSS before the I&A was created. Next slide, please. The sort of stuff that was published in the supplement, two organizations are prominent. One of them is General Electric, the other is UCL. At General Electric, Dudding had acquired an assistant called Janet. At UCL, Bernard Welch was a junior colleague of Pearson, and together here's some sample titles by Janet, Dudding, Welsh. In a way, the most sociologically interesting of the papers is a joint piece by Janet and Welsh, the third one there, because you've got these guys collaborating, an industrial person and an academic writing together. Next slide, please. Okay, so that was all going on quite smoothly. And then the war came in 1939, and that actually seemed to be the end for quality control in Britain. Why was it the end of quality control? Egon Pearson didn't go into wartime quality control. He went to the evaluation of weapons, not the production of weapons, working for the Ordnance Board. The supplement ceased operations for 42 to 45. Dudding and Janet continued GEC and in a section, but it's a much reduced section. And for Stewart, well, yeah, in a way, because his second book of 1939, Statistical Method from the Viewpoint of Quality Control, makes no impression. So it all looks pretty dismal for quality control in 1939. However, next slide. In 1942, there was a glorious spring with the creation of an organization called SR17, which is the Ministry of Supply's Advisory Service on Statistical Quality Control. The MOS basically controlled supply to the army. So weapons, uniform, everything that the army needed went through the Ministry of Supply. There's an American influence here, but it wasn't from the bottom up, it was from the top down. British politicians were asking, why aren't we doing the same as the Yanks? So they created SR17. SR17 was ginormous by British statistical standards, over 40 staff. At UCL before the war, there was probably one full-time equivalent working on quality control. The staff included many luminaries of post-war stats, Anscombe, Armitage, Barnard, Lindley, Plackett, Walker, etc. It produced more statisticians than any peacetime establishment. Next slide, please. This is what these guys and guysesses looked like 25 years on. So they were very well heeled, very well dressed. Nice banquet. Move on. Next slide, please. Lots of publications. One of the publications, I think, was mentioned a while ago. It was a revised version of Pearson's pre-war effort, BS 6000R by Dudding and Janet. Another one carries the Ministry of Supply imprimatur. Next slide. SR17 had two faces. One's described by Jeff Jarrett. He he basically went around ordnance factories to get them doing quality control. After the war, the section exploded. It's quite picturesque, so I quote it. After the war, the section exploded like a London bomb into statistical occupations all over the country. I was a piece of shrapnel that landed in Sheffield. Jarrett went from Sheffield Steel to University of Sheffield and then to New Zealand at Otago. Next slide, please. There's another phase to SR17 that Lindley fondly recalled. So basically they had an office in Baker Street. We went to the National Gallery concerts at midday, did the crimes crossword. It was like being a group of PhD students without a supervisor. So Lindley was a typical SR17 person. He was offered the choice on graduating in maths at Cambridge between going in infantry and going to SR17, so he took SR17. Although much practical work was done, the theorist worked under George Barnard, learning statistics, read all the big papers, and slowly began to understand what the subject was about. Next slide, please. Retrospects on all of this. Shewhart was, in a way, the second influential outsider who affected the course of statistics in Britain, the first being Ketterley in the original finding of the society. Shewhart joined the ASA in 1924. Unlike his British counterparts who didn't join the RSS until the I&A section was set up. But in the US, there was no E.S. Pearson or comparable involvement of academic statisticians in the war. In the war, there was the American version of SR17 or the American versions of SR17, which brought in masses of new people into statistics. Next slide, please. As a footnote, Shewhart became a fellow of the RSS, and Fisher, R.A. Fisher, who was the president of the society at the time, wrote to him saying, "I hope you'll take this election as a tribute to the esteem in which your work is held in this country." So, Shewhart got his recognition. There's quite a lot of literature. There's a massive amount of literature on Shewhart. On the next slide, I've got some of the things that illustrate the flavour. The participants, Dudding and Pearson, wrote up what had happened. There are histories, the histories, the Barnard and Plackett survey of stats in the Second World War as useful things. Both Barnard and Plackett were in SR17, and there's a thing I wrote about maths in the RSS, which stops really with the founding of the industrial and agricultural section in 1934. That's it. Thank you very much.
Yes, fascinating. Thank you very much, John. That's an excellent description of the history of all this stuff that went on. It's just amazing as background to the work that we've been doing since then. It's fantastic. Thank you very much. And our final talk is from Roland Colquitt now, who's going to look at some of the actual, stop sharing, practical aspects of using control charts, I believe. Roland, would you like to share your slides, or would you like me to put them up here?
Well, my slides are on my screen.
Right, you can have.
Are they on your screen?
No, you can try sharing them if you like.
I have.
Okay.
I have shared.
Right, and it looks like, are we going to see them? We might do.
Right. Share.
Wait. Might be. I think there's a lag because of various things.
I've been through this before, actually.
Yeah.
So,
Right, there's something on the screen now.
this,
Oh, it's the previous one. Right, sorry. That's funny, isn't it? Where's that come up? Oh, that's because it's the previous one. Right, okay. Right, you might try again. Might be okay. You've got a black screen with your name there. Try again. Would it be easier if I did it from here?
it might be.
Well, this is me putting it here. So share, you reckon share, presenting teams, is that?
I've now got the full presentation on my screen. It's how to get it down to you.
Try that. Press present now, so I think that's love that. Do it. After Shewhart.
Yeah. Can you see it, Roland?
Pardon?
Can everybody else see it?
Yeah, I can see it.
Okay.
I can see it.
Right, you're good to go, Roland.
Good to go?
Yeah.
Right, thank you very much. So I'm going to continue the story into the latter decades of the 20th century. I'm particularly interested in the period around about when SPC became everyone's very best friend. And the trigger for this was that in the 60s and 70s, products being produced in the West were revealed to be quite inferior to corresponding products being built in Japan. And this was quite alarming. It was affecting North America as well. Cameras, watches and cars were under terrible threat, and there was talk of legislation to limit such products coming from Japan. Now, the British government publicised this, and all the tabloids were full of it, and television programmes. And as a result of this publicity, there were many, many available courses in SPC, based on the writings, of course, of Shewhart and many of his followers, including Deming, a true guru, Wheeler, a sub-guru, and other people earning a great deal of money. So my concerns were at a much lower level. I went to BP Chemicals' factory in Hull to attend a meeting to advise people on some aspects of SPC. Before I could get to the room where the meeting was, I was met at the door by a process operator. Now, this person was in a place where process operators wouldn't normally be, so I was a little suspicious. And he said to me, some of the SPC charts that we're using here are absolutely ridiculous. That's pretty strong coming from a low-level person. In the chemical industry, of course, the processes are fiendishly complex. No one person understands what is happening, and they often disagree. But it's obvious that the process operators have some knowledge that the technicians and the managers do not have. So I was listening carefully to what he said. And he said, this is what my supervisor insists on us doing. On day one, we measure the quality of the product. On day two, we measure the quality of the product. On day three, we measure the quality of the product. Notice we haven't actually done anything. We haven't made any decisions. We haven't taken any actions. On day four, we now have this magic number 4 data points, and we can take action. We plot the mean of the 4 measurements on the mean chart, and the range of the 4 measurements on the range chart. And this is what was being done in the chemical industry, trying to imitate the great success that had happened in other organisations. So let's just go back to Shewhart for a moment. Shewhart's companies, Shewhart's place of work was so different from the chemical industry. And of course, in 50 years, the chemical industry had boomed. Telephones are obviously made by assembling components. The components are made of metal and hard plastic. They're solid. And it's in the assembly industries that Shewhart's procedures for quality control had proved very useful and were proving not so useful in the chemical industry. Shewhart's data fell into natural groups. Many of the data sets that he shows, the data falls nicely into groups of 4. And of course, if you have natural grouping, it's important to respect this. But many of the companies I was visiting were in the liquid industries. They call their processes continuous, but of course, all SPCs applied to processes, whether they be management processes, service processes, what have you. But in the liquid industries, that's chemistry, oil, etc., you get one-at-a-time data. You do not get naturally grouped data. We could talk about that for hours, but I've only 20 minutes. So the supervisor who's telling the operator what to do, where did he get his knowledge of SPC? He had been on a course. I suspect the course was one designed by people who had experience in the assembly industries, and they were attempting the impossible to apply the same procedure in the liquid industries. So I suggested to the operator, who was terribly worried about having data and not using it, I said, why not try an individuals chart? I told him what it was. He said he'd heard of it. Later that day, after my meeting, I saw the operator again. He sought me out. He said, my supervisor tells me I should not use the individuals chart. I should use the mean chart, because the mean chart is more powerful. Well, I had to agree, of course. A sample of 4 numbers is probably going to be superior in some way to a sample with only 1 number. So, in the liquid industries, chemistry, etc., they have one-at-a-time data, but they want to capture the power of having averages. Here's some one-at-a-time data. We are measuring time, the time taken to do certain things. Also very popular around the 70s, 80s, people were measuring time because if you can do things more quickly, which the Japanese were doing, then you can earn more money. So this data can obviously be put into an individuals chart. You've seen charts like this, very simple, very straightforward. The points in blue, that's the data. They're joined together by black lines. The green line in the centre is through the average of the data. And of course, we have the decision lines at 2 and 3 standard deviations. And of course, various gurus and semi-gurus from the past would say, this isn't right, you should be doing something slightly different. Right. So how do these liquid people increase the power of the individuals chart? They can add warning lines, which I suspect Shewhart didn't use. We can add additional decision rules, and that can smarten it up quite a lot. Somehow we need to calculate means. And it suddenly became popular to have a moving mean chart. When you get the data for day number 6, you average it with days 5, 4, and 3. Yeah. And we plot that. And these were becoming rather popular. Now, I was a statistician, and I could see pretty quickly that this was leading into trouble, because moving means are autocorrelated, for sure. And practical people don't use the word autocorrelated. So we had to start introducing them to the idea of autocorrelation, which is very big and it's quite a problem in the chemical industry. I'll just say in passing, so is skewness. If you're measuring impurity in chemicals, almost certainly you'll have a very skewed data set. This is autocorrelated. You show that to a manager or an operator in the chemical industry, they say, yeah, that's just what we have. We have the process drifting upwards at times, drifting downwards, drifting up again, and we're not at all sure why. But that is autocorrelated data. Of course, this is completely the different opposite problem. This is negative autocorrelation. I hope you haven't got that. So, quality managers are not familiar with autocorrelation. They're not familiar with the mathematics of autocorrelation, that's for sure. It's our duty to communicate with such people without using jargon or mathematics. So, I suggested a test for autocorrelation, not the sort of thing you have in your laptop. Simple. Count the number of times the data plot crosses the center line. The data plot, that's the black line that's bouncing up and down. How many times does it cross the center line? If we went back and looked at that individuals chart that I've just shown you, it crosses 21 times. Well, is that a lot? Is it a few? We need some standards to work to. So if that number of crossing the center line is very low, we must assume, or one possibility is that we've got positive autocorrelation, and the opposite if that number is more than the upper limit. Here's a table of standards. In that individuals chart, we had 50 points. So you would expect to find the black line crossing the green line somewhere between 19 and 32 points. If we went back to the autocorrelated data, that black line only crosses 11 times, which is much less than 19. So this is a very simple test. Operators like it. Now, there are lots and lots of different control charts you can use. These were springing up all over the place. You are familiar with this one, Shewhart's mean and range chart. This is a British standard. British standards are numerous and expensive, rather ugly, far too mathematical, but they are intended to help people who are doing things in manufacturing. You've already been listening for at least an hour to part 2 of this standard, so I don't want to say any more. I would love to talk about the exponentially weighted moving average chart. That is a moving average chart, which of course is automatically autocorrelated, but it became quite popular. If you know you've got autocorrelation and you get that standard, it tells you exactly where to put the lines to take account of the autocorrelation. I'd also like to talk about this one. Part 9 only arrived in about 2020. I was invited to the team writing this in about 2017. I didn't stay long. I pointed out, at the invitation of the chairman of the group, that what had been written was totally unacceptable to quality managers. But this final version in 2020, I would love to have in my hand a copy, but at £320 and my retirement, that rules it out completely. I would love to talk to you about the QSUM chart, because this illustrates certain features of gurus. Gurus are helpful though they are, and very capable though they also are very rigid, and they speak in terms of certainties. I detest certainties. Certainty is the enemy of, well, almost everything. It's the enemy of progress. It's the enemy of cooperation, etc., etc. And it's with the QSUM chart that we've seen many disputes between different gurus, different sub-gurus, and a lot of ordinary people like me who just use common sense. So I'm going now to switch. I'm going to have to miss a few slides. This is exponentially. I might have time to come back to that. I must get to the QSUM. The QSUM has been mentioned. It became very popular in ICI, Imperial Chemical Industries, back in the late 60s. It was very popular and very useful. At that time, the statisticians and the technicians were actually talking to managers. At that time, one of the world's greatest statisticians was working at ICI Dyestuffs division in Manchester. When I graduated, I went there as fast as I could, my legs would carry me, because I wanted to work with this person. It was George Box. Unfortunately, when I arrived on Monday, he had left the previous week. Wherever I go, standards seem to go down. So George had left. He went to Madison, Wisconsin, and had a very distinguished career there. I was left with the other statisticians, many, of course, very capable. Now, this was a QSUM chart, just the sort of thing an operator might draw around about late 60s. So it's very simple, but can be misleading. To plot a QSUM, you take the data. From each data point, you subtract a target value. And the difference between the data and the target, you add that to get a cumulative total with the previous differences. So it's a cumulative sum of differences from the target. And what we're looking for in a picture like that is the corners in the graph. After sample 13, it stops being horizontal and plunges down with a negative slope. From about 33 onwards, there's a positive slope. There are two corners in the data suggesting there are two changes, and it is a powerful chart, though dangerous in the wrong hands. I'll skip that. So, having found two change points, we now alter the individual's chart by drawing in these horizontal lines. And this is an extremely powerful graph. Managers can talk to workers with this on the table in between them. Very, very useful. You've heard from previous speakers a lot about eminent statisticians talking to other eminent statisticians, and so it should be. But it's also very important for managers and workers to talk to each other in a relaxed, casual environment. And often both parties learn quite a lot. So the QSUM chart is definitely powerful for detecting changes like that. So why am I getting so excited? I attended the annual conference of the British Deming Association on several occasions. I used to look forward to it. On one occasion, the guru's sub-guru, that's Donald Wheeler, said, the QSUM chart is a waste of time. It's no better than an individual's chart and it's quite misleading. I knew that not to be true. I leapt to my feet and was determined to put a stop to these lies. Or was it lies? I don't know. It was hard to believe that Donald Wheeler was a liar, and it was hard to believe that he was incompetent because he'd written many excellent books. So we had a discussion. Speaking more generally, then we'll come back to the QSUM. You must not expect any control chart to be perfect. They're not coming from God. If a process changes, hopefully the chart will detect the change, but it won't detect it immediately. You may have plotted 2, 3, 4, 5, 20 points before you get enough evidence of change. So you're going to get false negatives and false positives. I won't talk about that too much. We learned a lot about that during the epidemic. So, what do managers want? They want an early signal when a change occurs. Common sense says you're only going to get an early signal if it's a big change. A small change is much more difficult to detect. In addition, we do not want lots and lots of false alarms if the process is stable. Right. Now, the best way to measure the performance of a control chart, I think, is to calculate the length, the run length between a change occurring and it being detected via the chart. And the average run length is an indication of the power of the control chart. That's a nice simple slide. This is not so simple. I'm sorry to inflict it on you in one chunk, but I'm desperately short of time. This is telling us about 3 alternative charts that you might care to use. An individual's chart with action lines only, an individual's chart with action and warning lines, and the QSUM chart. The y-axis, the vertical axis, is the average run length. The lower numbers are powerful charts. Now, the time it takes to detect a change clearly depends very much on the size of change. That's on the x-axis. We've got 0 change, 1 standard deviation, 2 standard deviations, 3 standard deviations. With a step change of 3 standard deviations, that's an enormous change. All 3 charts would detect it almost immediately. Going right to the other extreme, if the process is stable, all 3 charts are roughly equal in performance. It's when you get a change of about 1 standard deviation that the QSUM chart is at its very best. That's a change of 1 standard deviation. Your individual's chart without warning lines takes about 47 points to detect a change. Senior managers in the chemical industry say this is too long. We can't wait 47 hours or 47 days. We've got to know much more quickly than that. But look where that red line cuts the QSUM line at about 10 or 11. So the QSUM chart is 4 or 5 times as fast as your individual's chart with action lines only. It speaks for itself. The QSUM chart, if you're a manager who wants to detect changes of 1 standard deviation, it's a winner. definitely. Now, I almost forgot his name. Wheeler, Deming's sub-guru, had used a set of data in which there was a step change of about 2.5 standard deviations. And I pointed this out to him. If he'd used a more realistic chart, the sort of charts that senior managers are interested in, it would have demonstrated the extreme power of the Q-sum. I point this out. Gurus are not to be 100% trusted. They occasionally say things based on the rigidity of their message, which is wrong. They tend to be dictators. Of course, there are lots and lots of gurus in other walks of life. There's about 20 wars going on at the moment, all of them inspired and led by gurus. So gurus can be rigid. I much prefer for people who are using control charts to think for themselves. If your chart isn't sensitive enough, you can move the lines in. Regardless of what Shewhart said or Deming says, you've got to make the chart serve your needs. Right. So the average run length, I think, is a very good metric. Going back to these, I don't have time to look at all of them. I'm looking at
2 minutes, Roland.
2 minutes. This is a supreme performance. I always overrun and Shirley gets always annoyed. I've almost finished. Let me just say, what do managers want? I've mixed with thousands of managers because I worked in the management centre of a university. Many managers wish to get early warning of changes. Of course they do. Large changes are more easy to detect. Many managers want to detect a medium-sized change, a small change of 1 standard deviation. That is worth money. It's big enough to be worth money, but it's small enough to get under the radar. As I've said, managers, whilst we're talking about them, do not want mathematics and do not want statistical jargon. And furthermore, many managers are now less interested in process control than in process improvement. That's the new scene where all the action is. So SPC charts are actually widely used by the practitioners of process improvement. So 100 years, we've seen a lot of change. 100 years ago, somebody's doing something to me. 100 years ago, time used to pass slowly. You won't remember that, of course, you're not old enough. Today, time has flown. We've had 4 speakers saying such wonderful things crammed into 2 hours. I'm sorry my presentation was so hurried, but it has to be so. You will actually have time to ask questions in the next session if you're still here. So thank you for your attention.
Thank you. Thanks. Excellent. Thank you very much. Gosh, so Q-sum. Moving on. That's brilliant. So we've had 4 completely different talks. I'd really like to hear a comment from anyone on the online or from the audience here. People that were speaking before. Do you use the Q-sum, for example?
We are beginning to use it. Obviously, the national team looking at neonatal deaths and stillbirths are using Q-sum as part of their. We tend to avoid using it, though. I'm about to develop it. I have just written a new tool, Q-sum, for the surgical team to do that. We'll see how that goes. That's up with that application. There's a lot of specialist knowledge you have to put into a Q-sum tool to make it useful. I need to get that from the practitioners rather than straight from
Okay, thank you. Blaise, comment.
I was asked some years ago by a senior director to look at ET's key performance indicators, which have a rather large number, like the big key. They were basically interested in knowing when the key performance indicators were changing. Well, is this getting better? Is this getting worse? And I rapidly concluded that managers were overreacting to the noise in the data rather than the signal. Having read stuff from David Spiegelhalter about his use of Q-summons in the aftermath of the shipment inquiry, foreigners, we had a serial killer doctor some time back, and he's killing off a number of his patients. Spiegelhalter in the subsequent report suggests that one could look at the death rate of doctors using Q-sum charts. So I was interested in Q-sum charts, and I used them very successfully for key performance indicators in BT. I was using the R package QCC, which would enable you to not just plot them, but actually mark the ones that are statistically significant, and therefore management would not respond to things that were just noise. And that worked very successfully. So I completely agree with the new tendency of Q-sum charts.
I'm completely agree with that. Whenever we do charts, all the charts we produce and all the methods we use, we mark statistical significance. So our users see on the chart when we've got statistical significance, however we define it. So they don't have to count points, they don't have to make it up for themselves. It is highlighted on the chart, so that's a really helpful thing to do.
Okay, thank you. Any other comments or questions? Anything from the speakers that would like to say? Penny, would you like to give us something up? Comment if you're able to unmute and speak.
Whoops, change my screen over. No, I really enjoyed all those presentations, especially the practical aspects. I mean, I do remember Spiegelhalter's suggestion that a variant of sequential ratio could be used to detect Harold shipment earlier than it was, but again, that was, I don't know.
Okay, thank you. John, have you any additional word? Jonathan? You have to unmute first of all.
Yeah, I was wondering how common or whether it happened at all, whether there are misunderstandings about other countries' success. So obviously lots of talk about Japan, but in the Second World War, Britain seemed convinced that American industry owed its success to quality control. But my impression is that quality control wasn't actually important in American Bell Telephones industries at all, and until much later, and then it only became important under the influence of Japanese. And I just the international transmission of these ideas, I think, is quite interesting, and that's what I wanted to say.
Okay, thank you. And we have a question. Alan Hodge, would you like to just unmute and make your comment, and then Jackie, and then we should conclude. Alan.
Yeah, thank you very much. Very interesting, all of the presentations. I come out of the construction industry. Our activities are based on the programs of most projects that used to be sort of 18 months at a time. So every individual activity was only 3 weeks or 3 months. So you only got a very small amount of data over a relatively short period. So managers in those businesses need some feedback rapidly, which is the point I think Roland was making, and others. Back in the 70s, the ready mix industry relied heavily on QSUM. And I really don't understand. You've given me a quick introduction to it again, and I remember it being about the differences. And it always struck me as a bit odd that you'd get a target strength for concrete, say 30 newtons, and they were plotting the differences for that, and they had a mask that they used to put over, and the which was always, oh yes, everything's all right, but we were getting cube failures, strength failures, but everything with their samples was okay. So I was very, very wary of QSUM, and have not even thought about using it again in the last few years.
That's a very controversial little comment there, Alan. So thank you. We'll just note that. I do want to finish at 5+5. So Jackie, would you like to give your comment quickly?
My question is mostly directed to John, but maybe other people know about this. Some of those old books and guides, I mean, where are they physically? Were they, I mean, maybe they're scanned and available, in particular those sort of short guides that they came up with, not the huge fat book. I'm just curious, do librarians take care of all these books for us?
Yeah, I posted them, all the references I could find at the end of my talk, but the Indian Statistical Institute has all of Shewart's stuff online.
Oh, nice.
And you can still find his books online as well. I found several different copies. But yeah, check out the Indian Statistical Institute first.
Thanks. And what about those short guides that they came up with the SR17 team? Are those preserved somewhere?
I think they're in I think libraries have them, for example, but things take searching for. Okay. I discovered in Glasgow, I think, a complete series of the SR17 discussion papers.
Ah, okay.
I've forgotten the exact detail, the exact reference, but libraries have them. You see them if you put them into Bookfinder. You can buy second-hand copies of them.
What we'll do is we'll get all the information together, and we'll produce some guide to where to get the information from.
Yeah, and we'll post that out after the event. Thank you very much. I'd like to thank everyone for joining the event, and it's been really interesting, fascinating detail, and a fantastic combination of history and practicality. Thank you very much, all the speakers. And as I say, we will be contacting the attendees and giving you a sort of summary of where to find these things and so on. So thank you very much for attending, and I'll close the meeting there. Thank you.
Thank you.